So thank you very much. It's a real pleasure to be here. The title of this session is Widefield Surveys, and from the meeting being focused on transients, I'm focusing this on time domain surveys. And then the talk title that I was assigned was High Frequency Surveys. So there are sort of three modifiers on the word surveys there. There's Widefield, there's time domain, and there's high frequency. And I will talk about at least two of those at every time, but I may sometimes skip in and out about the third one. So I'll talk about Widefield, time domain, not necessarily high frequency, et cetera. And I think the next talk will also help delve deeper into some of the physics that I'm going to talk about and explore more of the upcoming technology, especially at the lowest frequencies. So the radio time domain has been a very productive area over the last 20 years, but it has really been a regime where the results are limited by technology. So there's really exciting stuff coming from single dish radio telescopes like the FRBS we heard about earlier in the meeting. But the problem with single dish radio telescopes is that while they have a very wide field of view and are fantastic at capturing fast phenomena, they have poor resolution. So if you're looking for slower things, your sensitivity is very much limited by source confusion. And when you find those fast things, you have a very hard time figuring out where they came from. Hence all the confusion about where do the FRBs originate from, what are their host galaxies, redshifts, and all that. At the other extreme, we also have interferometers. And these are very sensitive and are capable of making extremely detailed maps of the radio sky, but they have rather limited fields of view and don't have the best ability to cover wide areas very rapidly. So what that means is that most explorations of the time domain radio sky outside of the regime of fast pulsar surveys have been targeted follow-up. And these have been very productive, but they haven't really been surveying the sky for new phenomena. They've been finding things that you identify at high energies, at radio wavelengths, or even now with multi-messenger astronomy, and trying to see what do those look like in the radio regime. So things like Gammaray Burst afterglows, relativistic supernovae, soft gamma ray repeater flares, brown dwarfs, tidal disruption events, X-ray binaries, extreme scattering events, and unknown objects that Greg will discuss in a little bit more detail. All of those things have been explored with very interesting and important results coming from the radio regime, but they've largely been driven by observations or discoveries at other wavelengths. There have been a number of blind searches over the last few years to decade, but they've been somewhat limited in their impact. They've used existing large-scale surveys, and that has meant that they've either had a limited cadence, a limited field of view, or both. And they've had some successes, but those successes have been limited. The interpretation is ambiguous, often because you're finding the events years or decades after the data were taken. Follow-up is challenging, often for the same reasons. And interferometry is a regime where trying to identify the outlier events, the extreme sort of 8 sigma or 10 sigma outliers, can be very challenging. And you have to make sure that you have very good control over your data quality and that you're not just finding the sort of anomalous artifacts in your data rather than truly interesting sources. But these have had influence. They have found useful results, such as constraining the orphan GRB rate. But right now, we're really entering a regime where there's a next generation of wide field explorations of the radio sky that are coming online, that are either online now or will be online in the next few years, that we hope to really revolutionize this field. So all the way from LOFAR in the Netherlands, the long wavelength array in the Southwest, Meerkat in Australia, ASCAP in Australia, Meerkat in South Africa, ASCAP in Australia, the EVLA in New Mexico, the ATA in California, or the one that I'm going to mostly talk about is the MWA in Australia. These are really revolutionizing how we see the wide field radio sky. So the two that I'm working on most directly here are ASCAP and the MWA, but I'll try to touch on some of the results from other surveys as well, and Greg will cover some other of this parameter space in his next talk. I just want to clarify, though, that these are only the imaging arrays. There is also a new generation of non-imaging arrays that will be fantastic for doing fast transients along with cosmology. So we heard from Vicky about CHIME. There's also the Molonglo telescope, Tianlai in China, and the Hera array. And these will also all help us understand the regime of fast radio transients and hopefully find some new and interesting objects as well. So we're talking about wide field surveys, so we can plot the parameters of these surveys on this chart here, where wide field is to the right and deep is going up. And the surveys that we're going to talk about are the ones over here. So things like the MWA, ASCAP, LOFAR, LWA I think didn't exist when this plot was made, but it's way at the end over here. And these surveys are really pushing the regime of wide field, going from hundreds to thousands to tens of thousands of square degrees in a single snapshot. So your discovery metric, simply put, will be some product of your telescope area that controls how deep you can go, your field of view that controls how wide you can go, and then your total integration time divided by your cadence. So we can either push the collecting area of the telescopes to go deeper, or the field of view to go wider. And some product of that will help us maximize our discovery. But exactly where that comes in actually depends somewhat on the details of the source, as I'll discuss later. So the Murchison wide field array is the one that I'm going to talk about for a few slides here. So that's located over here. So we're working at low radio frequencies, but still higher than some of the stuff that Greg's going to talk about. Fields of view of hundreds to 1,000 square degrees. Not super sensitive, although we're working on that. In terms of a parameter space, we've seen a number of parameter space plots for optical transients showing the time scale versus the luminosity of the transients. This is the equivalent in the radio domain. So we have slower and faster transients, brighter and fainter objects. And this is divided into two halves along these diagonal lines. Those diagonal lines are approximate limits of brightness temperature, where things that are over the 10 to the 12 Kelvin limit are presumed to have some sort of coherent mechanism operating, and things below that limit can be incoherent. And so you can see that we have a wide range. This diagram is pretty well populated. There are pretty big gaps, but there are things in many, many quarters, and they occupy sort of 10, 15 orders of magnitude in both axes. We go all the way from the fast radio burst here to bursts from flare stars, brown dwarfs, Jupiter, and solar-type stars, and they really span an extremely wide range of parameter space. And there's a lot of interesting physics. I'll talk about a couple of these things. Greg will talk about more. So this is sort of a theorist view of things. There's also a more observational dividing line that we can put on this plot, and that is where you divide things where you can look at them sort of from an imaging standpoint, where you make repeated images of the sky and look for things that change, to where you have to use faster techniques, such as doing pulsar-type observing or coherent beam forming that will allow you to really probe the fastest timescales. There's no sort of physical limit there. It just comes down to practicalities of how you process your data. So there are many goals that you can, if you look at these sort of types of variable sources on this diagram, there are many different types of objects you could hope to probe with these surveys and come up with sort of motivating physics reasons for why you want to look at these. If we could localize FRBS, as we heard about, we could tell what they're coming from, what their redshift is, look for the baryons in the universe, try to understand the energetics. We might also want to search for prompt emission from multi-messenger transients, the types of gravitational wave sources that we've heard about earlier. Look for orphan GRB afterglows, tidal disruption events without seeing corresponding high energy or optical triggers. Broader and less biased samples of relativistic supernovae. Look at strange pulsars, look at stellar and substellar flares. Directly observe extrasolar giant planets. Probe inhomogeneities in the interstellar medium and closer plasmas, the interplanetary medium, and even the ionosphere through scintillation and extreme scattering events. Look for state changes in X-ray binaries to track the disk-jet connection and understand how accretion proceeds on small scales. Do the same thing at large scales, look at AGN variability, connect to accretion changes or binarity, hopefully connecting to some of the talks we heard about in the previous session. And then finally, new classes of events. So there have been many papers on this. I list a few of them here. Many of them have been written by people in this audience. All these things are things that we can try to get at with these wide field radio surveys. I sort of have divided the types of sources that we might see into two different classes here and populated this diagram looking at the lower frequencies and the higher frequencies. Some of the things like pulsars you can see across the radio spectrum, they work everywhere. Other things like extrasolar planets are probably going to be best at the really low frequencies, as you'll hear about in the next talk. Some things really don't work too well at the low frequencies. Synchrotron blast waves, as we heard about from Brian Metzger, are really going to be delayed and self-absorbed at the low frequencies, and they're going to be hard to do. So if I can put my Shri hat on for a moment, it's a very uncomfortable hat, but I'll wear it for this slide, and just sort of say, okay, these are the science topics you claim to be able to do. Should I care? Well, Shri would probably say that pulsars are boring, unless you've come back around to the pulsar camp. Where are you in your cycle tree? X-ray binaries and AGN are mostly boring unless they're merging black holes. Scintillation, mostly boring, things like that. Other things on here, well, they're not necessarily boring, they're just very, very hard. So things like extrasolar planets, we're going to hear about in the next talk. It takes a lot of work, a lot of effort to do it properly. Other things on here would be really fantastic if we could find them. You might just think that they're unlikely from sort of a priori physics reasons, like looking for a prompt emission from Gammaray Burst or binary black hole mergers. Things that you got to look. There are papers that predict them, but they may be sort of unlikely. And then at low frequencies, again, the synchrotron blast waves are going to be self-absorbed, faint, and slow. But how does this all play out? What types of things can we actually find? There was a nice paper done a year ago by Brian Ito and Peter Williams, sort of parameterizing all this, at least for the synchrotron blast waves, saying, okay, we have a similar picture here in a wide variety of scenarios. You dump a bunch of energy in a small volume, that energy propagates outwards, it slams into some surrounding medium, and through synchrotron processes, it will emit a lot of that energy into the radio regime. Now, the exact details of this depend on how much energy, over what area, into what medium, all that stuff. But how can you find these things? These are things that we know exist. They've been studied at great detail with pointed observations. Can we do these things with blind surveys? Turns out that it's hard, because as your frequency goes up, your field of view gets down. So it becomes much harder to find these things if you don't know where to look in advance. But as your frequency goes down and you get wider fields of view, then the sources evolve on longer time scales, and they're much fainter and harder to find. So you need better telescopes, more sophisticated signal processing to get them. But when you churn through all the numbers, you predict modest numbers of these sources over a wide variety of physics scenarios with the next generation of surveys. This is a nice summary slide that Brian and collaborators put together, showing that going all the way from ultra-high frequencies, what I basically consider sort of millimeter stuff, down to the sort of centimeter wavelengths, down to meter wavelengths. You see over here at the centimeter wavelengths with telescopes such as the VLA Sky Survey that I'll talk about and the VAST project that I'll talk about, you can get sort of few to tens of some of these various classes of events, long GRBs, tidal disruption events, neutron star mergers with magnetic fields, and all that sort of stuff. So what are these surveys, and what are they actually doing? So the survey that I've been most involved with is the Murchison Wide Field Array. This is a low-frequency radio telescope located in Australia. We currently have 128 tiles, each of which has 16 dual polarization dipoles. We operate over the frequency 80 to 300 megahertz. That's either high frequency if you're Greg, or low frequency if you're everybody else in the room. Our bandwidth is 30 megahertz. Our resolution is modest, only about an arc minute, but it's still plenty good enough to get good localization of, say, an FRB if we could see one. Our field of view is really what sets us apart. We have about 1,000 square degrees instantaneous field of view depending on frequency. This is a drone's eye footage of our site. The other thing that really makes us impressive is our location. So we're at this very radio quiet site, this Australian SKA site, which is protected from radio frequency interference. So this shows the area and the population of the region in which all these different radio telescopes live. So MWA lives down here in a region that has about 100 people in an area the size of Massachusetts. So if only we occupied Massachusetts, that would be like the MWA. And that means that you're very, very free from interference, which, as we heard about with the FRB and Periton debacle, can cause all sorts of interesting transient events. But if we're getting rid of it, it makes our life much easier. So we're at about 1 milliperson per square kilometer, or something like a big toe per square kilometer. That's not to say that all these other telescopes have a hopeless task. It just becomes harder. You have to put more energy into getting your signal processing, your amplifiers, resolving all the nonlinearities, doing your RFI excision. It's a solvable task, but it just makes things harder. So we decided to, instead of put all the effort in there, to put all the effort into fighting off exotic spiders and lizards and snakes. So the MWA was commissioned a few years ago. We've been taking data pretty steadily since then. Here is a single night drift scan of the entire sky. So this is basically one pointing where we just let the sky drift overhead. It's a little hard to see with the lights on, but it's about 40 degrees in declination top to bottom. Some of your favorite sources might be in here, things like Centaurus A radio galaxy with its giant lobes, and the Vela Puppis region over there. You see a lot of diffuse emission. That's real. That's all variations in the synchrotron emission from our galaxy. There are a lot of people interested in studying that. And then basically every other point source you see is an AGN. So if you're looking at trying to identify long-term statistics of AGN and things like that, we're going to give you a very good resource. So very shortly, we have coming out our first large-scale survey product from the MWA. We've had a number of sort of smaller product papers out in the last few years, but we have Gleam, which I'm not going to even try to mangle the acronym for you, but it's basically an all-sky, all-frequency survey, and the first extragalactic data release is coming out. The paper's been submitted with a few 100,000 sources down to an RMS noise of about 8 millijanskis, with 20 different subbands across our bands. So you get a lot of great spectral information. So if you're looking for information on any sort of source that emits at low radio frequencies, it'll be available. Right now, we're excluding the galactic plane from this. There's a whole lot of really fantastic, rich information in the galactic plane. It just is a lot harder to do. So we're working right now on processing the galactic plane to get all this information out about the supernova remnants, H2 regions, diffuse synchrotron emission, X-ray binaries, pulsars, and all that. But that'll come out slightly later. Okay, so this is a view of the low frequency sky. This is a static view. This is our all sky survey. But this is a talk about time domain science. Now, we started this game. We were commissioned 3 years ago. We've been doing commissioning science for a few years past that. The LOFAR telescope in the Netherlands has been operating for about 8 years. Why haven't you heard about fantastic radio transients found at low frequencies? Well, the answer is that the low frequency sky, -1. That's just saying that those are, those are basically uniform weighting, close to uniform weighting. So that, for the non-radio astronomers, that emphasizes the point sources, which is great if you want to look at point source statistics. If you're interested in, say, the ISM or H2 regions, you might be interested more in different mappings of our data that emphasize the diffuse structure, so more like natural weighting. So we're doing that. It's just taking a while. Yeah, so the low frequency sky has turned out to be remarkably boring. Now, at some level, this makes our job easier, right? When you look in the optical sky, you see things going off everywhere, and identifying the right object is really difficult. But in the low frequency sky, things are a lot harder. So Greg will talk about this in a bit more detail. But for instance, in this LOFAR MSQ paper by Stewart et al., they had about 2,000 epochs of 175 square degrees each, and they found one mostly convincing transient candidate. If you did the same survey in the optical, well, you'd find sort of tens of thousands of objects. And this one is even a bit hard to understand because it's a pretty bright object. That implies that if you extrapolate it to other surveys, you'd see tens or hundreds of these. So whether or not it's really a transient or an artifact, I think remains to be seen. They make a pretty convincing case in this paper, but there's still more work to be done. We've done some similar work. We have a paper right now that we're working on with Tara Murphy is leading it, comparing the Gleam data to some very nice work from Dale Frail and collaborators using a sky survey at the same frequency from the GMRT telescope. So this is comparing two surveys of the sky about 3 to 4 years apart. So we compared about 100,000 sources, and we came up with 2 transient candidates, one of which we identified as an artifact. The other may or may not be real. Dale's collaborator, who's an expert in the GMRT data, thinks it's real. We're still looking for more data to try to really understand that. So that would be about one source in 16,000 square degrees, varying over a timescale of a few years. So the surveys are very, very clean. We're in the regime that we're not limited by artifacts and by processing uncertainties and things like that. The data products are really fantastic. What we're limited by is just the fact that the sky isn't changing. Sometimes, if you look at, so I'll talk about this in a bit more detail, but that's perhaps not unexpected. Most of the high latitude extragalactic sources that you see in the sky aren't really doing much on these timescales. We do see a number of interesting sources, things that are varying, but most of them are things like this, which is a nulling pulsar. It's completely gone, it comes back, it goes away, it comes back. We don't know why that happens, but if I asked most people in this room, they'd say, who cares? So I find that interesting, but they're not sort of unknown new classes of objects. They're not telling us about the explosions and things that we heard about before. Nonetheless, the limit in this parameter space that we get from this survey is pretty interesting. So this is a parameter space showing the flux of the source against the sort of aerial rate. So more common, less common, bright, faint, sort of a slightly different parameterization of the plot I showed before. And this is coming from, again, Brian Metzger's paper, predicting things for 150 megahertz. And all these different lines and different predictions for the different source classes that Brian, Ido, and Peter encountered. You could read the various acronyms and do it here. And so we're right here. So we're right at the limit where if we had seen a magnetar flare go off, we know those things only happen once every few years, and they tend to happen at low latitudes where we weren't looking. But if we had seen a magnetar flare go off, we might have expected to see it. But getting down to these normal classes of events, things that we know happen once a day, once a week, once a month, we're not quite getting there yet, but we're getting pretty close. There are 2 ways to fix this, 2 ways to change the survey such that our star here will start hitting these lines. We could try to go deeper. That's definitely something that we're working on now, or we could try to get more sky coverage. That's hard because we're limited by sky area for the sky coverage, and in terms of going deeper, we're limited by telescopes and processing. So what's the point? Why do we care? Well, we need to go deeper, wider, higher frequencies are smarter. So we can look at FRBs. FRBs are interesting sources. We heard a lot about them before. It might be that we should go to wider surveys with lower frequencies where we might be able to find them. Unfortunately, no surveys have seen these at frequencies lower than 100 megahertz. Vicky showed 300 megahertz before. We have some other results at 150 megahertz, and we haven't seen them. These give some strong limits on either the population of the FRBs, their spectral behavior, their scattering behavior, or some combination. Another technique we can do is we can look at shadowing other telescopes that are finding FRBs. So while Parkes is staring over here, we'll stare at the same patch of the sky. When they find an FRB, we'll say, okay, did we see it? And we've done this experiment. So far, we haven't seen any things. The results are not super constraining so far, but we're still working on it. We can also take advantage of our wide field of view to look for multi-messenger transients. Here's a short Gammaray burst where we got on sky within 23 seconds of the X-rays hitting Swift. Sorry, the gamma rays hitting Swift. We didn't see any signal. It was pretty far away, probably not surprising. We've also done searches for high energy neutrinos. There we go, high energy neutrinos, and gamma ray and gravitational wave transients. So the limits from the MWA are these big circles on here. Sorry about that. Computer's being slow. Okay, so the limits from the MWA are these big circles on here. There are also smaller circles that are limits from the ASCAP survey that I'll talk about in a second. This was coming a couple days later because of the processing challenges involved. What we really want to do is get the MWA on it as soon as possible, within seconds to minutes, and then follow it up with ASCAP weeks, months, years later. Low frequency observing is complicated. We have to worry about the ionosphere that moves things around, sort of like seeing in the optical. It can be interesting, and you could study it for its own right, but it's still a difficult thing to do. You have to worry about that you're basically always looking at the entire sky, and you have to understand the response to your primary beam. You have to worry about the fact that you're always confusional emitted. There are always sources everywhere you look. You have an enormous amount of data coming through your telescope, and it's very difficult to process. There are also just challenges coming with operating at a remote site where there are various things that can try to eat you or try to eat your telescope. Higher frequencies is a very promising regime where people are working right now. There's a very nice project with Greg Hallinan, Dale Frail, and collaborators led by Kunal Mooley. The problem with the VLA is that its field of view is somewhat limited. It's only a couple tenths of a square degree, so it's not going to be able to get the really huge instantaneous coverage of the survey that I was just talking about. But it's really sensitive, so it can do a lot of really great work. So Kunal's been working on the Stripe 82 project, where they have a few hundred pointings with many epochs, or about 5 epochs. And they found mostly variability from AGN, a couple of stellar objects. There's also the Chiles Verdes project, where you could talk to Cherie about it. They're looking really, really deep, concentrating on the cosmos field, where they have fantastic multi-wavelength coverage. They have a few hundred variable objects, and Cherie is the best one to talk about that. The VLA Sky Survey is hopefully going to start next year. They're going to cover the entire sky to fantastic depth within the next few years. And there are white papers written by people in this room talking about the various time domain science you'll do with that survey. So the VLA Sky Survey is pushing all the way down to here on this parameter space plot. And there's new technology that will change things with the non-imaging surveys we heard about before, and then smaller dishes with phased arrays, as I'll discuss very briefly. So ASCAP is a new survey telescope in Australia at the same site as the MWA. The really special stuff is that we have this phased array feed that gives us a wide field of view, and that enables us to do new types of science. So there are some problems with how well it performs, but it's able to cover 150 square degrees pretty quickly, not to a fantastic depth yet, but we're working on that. So there's science that we're going to be doing over the next few years with the ASCAP telescope. Early science is starting later this year, and we hope to have really interesting stuff coming out. For instance, with the full VAST, we could locate tens of neutron-star mergers with arc-second localization. So wide field surveys are entering maturity at low frequencies, and at higher frequencies they're about to really start in earnest. But there's still a lot of work to be done in calibration and operations to push our processing toward the real time where we can send alerts out to the rest of you. The successes to date have been limited. Should we push on the cadence, the field of view, the depth, all three? Where do we put our efforts? So the MWA is changing its hardware a bit. We're upgrading. We're moving from our compact array to an array with double the baselines, which will give us much better sensitivity, and also an array with these really compact configurations that will give much better sensitivity to fast transients. And then we're merging into the square kilometer array. It's already attached as a tile 129. ASCAP is going to be going into production mode soon, and the VLA Sky Survey will be starting over the next year. Thank you.
So Dave, you may have noticed that in our paper, the title had part 1. So part 2 hopefully will come out at some point soon. But the point of part 2 is to address the question that, at least with the synchrotron transients, the problem of, even if you can find them, which is proving to be as difficult as we predicted, without context, it's actually hard to interpret what it is that you're seeing, because what the synchrotron emission is telling you is giving you some information about the energy content and perhaps whether the source was relativistic or not, but even that's not clear. And so the advantage of doing the follow-up work in the radio is that at least then you know what you're following up and you can interpret the radio emission in some framework. But I think one of the challenges is, even if you found sources, how do you connect them to what those events actually are? You know, how do you tell apart an off-axis jet from a TDE from an off-axis jet from a GRB?
No, that's right. And I don't disagree. First of all, I was not at all saying that the follow-up is not valuable. I think it's been producing fantastic results. But it's giving us clearly an intentionally biased view of the sky. And I think it's worth trying to see what we can understand. You're right, it's going to be hard. The synchrotron sort of process is pretty generic, and it hides a lot of the information about what the central engine is. But we've also heard a lot about similar situations in the optical where we see a transient source and just what's going on inside, or just what's going on inside extended emission from short Gammaray bursts could be hiding a lot of that central engine information. So I think I think it's going to be a challenging field, but I don't think that it's something that is without value. I think doing the simultaneous multi-wavelength coverage, as has been done, for instance, by Kunal and his Stripe 82 survey, will tell you a lot about what is or what isn't producing that, and then getting simultaneous high energy coverage will be great. But at some level, there are other things that we're also looking for at the same time, and we're going to find these things once we go deep enough. So the question is not so much why, but how, and hopefully that's something that your paper will address, and I know other people are also working on similar work.
You weren't around 45 years ago.
I was not.
But your comment about radio astronomy making great advances in the last 20 years, there were great advances made much earlier than that.
There were.
For example, when VLBI was first developed in the late 60s, discovered superluminal motion, discovered jets on quasars and things like that. So I just wanted to broaden people's perspective a little beyond the last 20 years.
No, I completely agree. I think, radio astronomy has had several golden ages. And I think, personally, have many collaborators who are around, like Ron Eakers, who constantly gives us history lessons. And we actually had an FRB search in our data, and we found something which turned out to be at a dispersion measure of 0. It turned out to be interplanetary scintillation that we rediscovered. So I had to go back and read all of the original papers on that, and then including Margaret Clark's thesis on that. So I completely agree, and we're really rediscovering a lot of the same phenomena in entirely different ways many years later.
When you work at the 100 megahertz, obviously synchrotron self-absorption limits your ability to see sources that are variable on a short time scale.
I agree. I think that's
probably the main issue.
Right, and that was in fact basically what I said, that most things, if it's a synchrotron process, whether it's synchrotron self-absorption or even possibly free absorption, you have to worry a lot about that, except for things like pulsars, brown dwarfs, things like that, where you're seeing sort of directly into the magnetosphere.
Thank you very much.